Alrighty, good morning everybody. Welcome back to Math 105. Plan for today is we're going to finish off Standard 15 by talking about briefly about Proposition 6. And then we're going to jump into Standard 16, which is going to be about Proposition number 9. So I've got my usual office hours next couple days. Today at 10 o'clock and at 2, tomorrow at 10 and at 1:30. As far as homework goes, I posted the Standard 15 quiz. It is already up, and it will be due on Wednesday evening. And again, as a reminder, Exam 3 is going to be this Friday, and will be over Standards 1 through 15. And will be similar in format to the last ones, and so we will not be having class on Friday. Any questions or comments before we get started for today? A chemist, an engineer, and a mathematician all one day stumbled across a pile of beer cans. But unfortunately, they're the old-fashioned cans that don't have the little tab at the top that make it easy to open. So one of them proposed that they split up and all find can openers. So the chemist goes to his lab and concocts a magical chemical that dissolves the top of the can in an instant and then immediately evaporates, so the beer is not affected. The engineer goes to her workshop and created a new hyper opener that opens 25 cans a second. Chemist and engineer are both pretty pleased with themselves. They go back to the pile with their inventions and find the mathematician finishing off the last can of beer. And they ask her in astonishment, "Whoa, how'd you do that?" Mathematician answered, "Oh, that was easy. I just assumed that they were open and started drinking." Okay, so if you recall, Standard 15 was kind of the standard about triangles. And we looked at, in class on Friday, several different triangle-related propositions. Propositions which are all about the idea that how do you show two triangles are equal to each other, only knowing partial pieces of information. So that led to a discussion of like side, 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 angle, and angle, side, as well as a couple that didn't work. And I wanted to start off class today with one more proposition related to triangles, not about necessarily showing two triangles are equal to each other, but instead looking at properties of single triangles where we have angles that are equal to each other. Specifically, if I drew out a triangle like this, let's say we had an A, a B, and a C. Like so. And if we knew that the angles at B and the angles at C are going to be equal to each other, which two sides of this triangle would you expect would also be equal? We have a triangle like this where we have two angles that are equal. Any ideas on which two sides of this triangle you would expect would have to be equal to each other from this? Yeah, AB and AC. The sides that are opposite the two angles, the two equal angles. And that's going to be, in fact, Euclid's proposition number 6, is that if you have a triangle where you have two equal angles like this, then the sides that subtend those angles, meaning the two sides AB and AC that are opposite these two angles, are going to have to also be equal. So proposition 6 is going to say that if in a triangle two angles be equal to each other, the sides which subtend the equal angles must also be equal. So in other words, in a triangle like this with angle B equal to angle C, it's going to have to be the case that AB and AC will also be equal. So to start this off, we've got Euclid's usual stuff, where we're just going to label the different sides and angles of the triangle. We're going to let ABC be a triangle with the angle ABC equal to the angle ACB. I say that AB equals AC as well. So in other words, Euclid's just starting off the way he usually does, just kind of setting everything up and saying, here's the triangle we're going to look at, and here's the claim I'm going to make, that AB has to be equal to AC. And now in his next line, Euclid's going to do something a little bit interesting. He's going to assume that AB is not equal to AC. We say, for if AB is not equal AC. If Euclid's assuming that AB is not equal to AC, what do you think he's going to hope to show under that circumstance?
That there would be a contradiction under that circumstance that doesn't work out.
Yeah, he's going to want to show that if AB and AC are not equal to each other, that that something is going to eventually break. Something is going to happen which should not be able to happen. Yeah, that's exactly right. And what do we call this type of proof? Which we last saw way back in Standard 9, where we assume the opposite of what we'd like to show, and then show that that arrives at a contradiction somewhere along the line.
I could be wrong, but I think it's disjunctive syllogism.
It's not a law of disjunctive syllogism.
That's just the word that came to mind. I don't know.
That was a technique from Standard 6 that basically, it's related to this, the idea that, if it's not one, then it has to be if one of two things is true and it's not one, it has to be the other. You're not wrong. That's definitely something that's heavily related here. But what was the name for the proof technique specifically that we had that was related to that?
Was it reductio ad absurdum?
Yeah.
Exactly. Yeah, so this is going to be, in fact, Euclid's first reductio ad absurdum proof. And this is the main reason I wanted to go over the proof of this proposition, because it turns out that in Euclid's Elements, this is the first one he doesn't just prove directly, he actually goes through and assumes the opposite and shows that leads to a contradiction. So he's going to assume and say, for if AB is not equal to AC, one of them is greater. Basically saying, if AB and AC don't have the same length, one of them is going to have to be longer than the other by definition. The only way neither of them is greater than the other is if they're both exactly the same. And here, we're definitely relying on the law of constructive syllogism to say, well, either they're equal or one of them is greater. We're assuming they're not both equal, therefore one of them must be greater. So for if AB and AC are not equal, one of them is greater. We're just going to say, let AB be greater. So we know that if AB and AC are not equal, one of them is greater. Euclid is saying let AB be greater because we know one of them is greater. It doesn't really matter which one. Euclid's going to pick AB to be the longer of the two sides. If AC turned out to actually be the greater side, then you basically just kind of swap AB and AC for the rest of the proof. So he's just he needs one of them to be greater than the other for his proof to work out, but which one it is doesn't really matter, because he could just always swap them out for the rest of the proof if AC was actually the greater one. So we're going to let AB be greater, and from AB, the greater, we're going to let DB be cut off equal to AC the less. So in other words, Euclid's saying, well, we're assuming that this AB line is bigger than the line AC. If AB is greater than AC, we actually have a proposition, which we proved last week, that says we should be able to find a point on the line AB, call it this point here, call that D, such that if we were to cut off the line AB at D, the line going from B to D should be equal to the length of the line from A to C. In other words, using the fact that we can cut off, that if we have two lines of different lengths, AB and AC, we should be able to cut off the longer line at a point D such that where it's been cut off from B to D is going to be equal to the length of the shorter line. Does anybody offhand remember which proposition allows us to do that? This is actually one of our ones from Standard 14. But which proposition was the one that allowed us to, when we had two lines of different lengths, cut off the longer one at a point that makes it equal to the shorter one?
Proposition 3.
Indeed. This one's going to be proposition 3. Actually, the last one in Standard 14 that we looked at. So we've cut off we've cut off AB at a point DB to make DB and AC the same length. And so now we're going to let DC be joined. By which Euclid just means draw the straight line going from D to C. And now, our goal is going to be to use side angle side to prove two triangles would have to be equal to each other that can't possibly be equal to each other. Specifically, we're going to have a goal here is to show that under these circumstances that the triangle ABC is going to be equal to the triangle DCB, which, as we'll discuss, can't possibly happen. Because if this can't happen, that means that we found a contradiction somewhere along the way, and our assumption that AB does not equal AC can't possibly have occurred. Let's see if we can do this. So we've joined DC. We want to show triangle ABC is equal to triangle DCB. And since this is proposition 6, which came before the propositions for side, 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 angle, and angle, angle, side, there's only one triangle equality proposition that's kind of left to us that we're able to use, and that being proposition 4, which was side, angle, side. So let's see if we can use side, angle, side to prove these two triangles are equal, ABC and DCB. Well, first of all, we can say that since DB is equal to AC and BC is common, the two sides DB and BC equal AC and BC respectively. So in other words, we know DB is equal to AC, which is something we've already said. We also know that these two triangles both share a common side of BC, which is going to just be equal to itself. So we have DB is equal to AC, and BC is equal to BC. So the last piece that we're going to need in order to be able to apply side angle side here is we're going to need to be able to find two angles, one in each triangle, one in the triangle ABC and one in the triangle DCB, that are equal to each other. So which pair of angles can we use that we know are going to be equal from our starting assumptions? Yeah,
Angle ABC and angle DBC.
angle ABC and angle DBC?
Yes, sir.
Okay. Those are, in fact, two angles that are equal to each other. This angle just really being equal to itself. However, if we knew that those two angles were equal to each other, or just saying that angle is equal to itself, I don't think we would be able to use side angle side. And why do you think that is? Why couldn't we use side angle side here in this circumstance?
Because the angle doesn't lie between the two sides, we know that are equal.
Yeah. It does. This angle does lie between the two equal sides in the triangle DBC. It's between this side and that side. But that angle is not equal to is not the angle between two equal sides in the other triangle, ABC. We know this side is equal, the right side is equal, the bottom side is equal, but the angle in between is not this angle right here. So we couldn't necessarily use side angle side just knowing this angle in ABC is equal to an angle in the other triangle, because this angle doesn't come in between AC and BC, the two sides that are equal to something in the other triangle. Does that make sense?
Yeah.
That is very certainly, though, will be an angle between an angle that in one triangle that is equal to an angle in the other triangle, and with the same angle. It's just not one that's going to be helpful for being able to use side angle side. So what can we try instead? An angle in this smaller triangle, DBC, that's equal to an angle in the triangle ABC. And hopefully an angle that allows us to use side angle side.
Well, the one in the smaller triangle has to be DBC.
Because that's
the
equal to.
larger triangle has to be ACB. Because if it's side angle side, those are the only options.
Yeah, those are the only two that would work. Do we know angle DBC is equal to angle ACB?
Yeah.
It certainly looks like I've drawn the little symbols that make it look that way. I would say we know those are equal by the very first line of our argument. That's the first thing we assume, is that angle ABC and angle ACB are equal. Here, using the fact that angle DBC and angle ABC come out to be the same angle. So I think that's the pair of angles we're going to use, be able to use alongside side angle side here. Equal to ABC, AC and BC respectively. And the angle DBC equals angle ACB by our very first line. And thus, the base DC equals the base AB, and the triangle DBC will equal the triangle ACB. And that is coming from side angle side, or, and Euclid refers to it just as proposition number 4. Because we have two pairs of equal sides, DB is equal to AC, BC is equal to itself, and the angle in between the angles in between those two equal pairs of sides, the angle at B here and the angle at C here, are going to be equal. So by side angle side, the two triangles DBC and ACB will have to be equal. What's wrong with that? What's wrong, though, with saying that DBC and ACB are equal to each other? I wrote down on the board that that can't happen, but why should that not be allowed to happen?
Because if those two were equal, then by side angle side, I think BC would have to be equal to like AB, or is it DC would have to be equal to AB? One of the really short, I'm having a hard time, it's
a little bit hard because they're kind of flipped around, which triangles are equal.
One of the really shorter ones would have to, basically the two triangles would have to be, one of the really short sides would have to be equal to AB.
So you're saying that DB would have to be equal to AB? Kind of the last, well, I don't think DB would have to be equal to AB.
DC.
I think DC and AC, which are kind of the last two, well, let me see. DC would have to be equal to AB.
Yeah.
Can that happen? DC equal to AB? And why not?
Because, I'm trying to figure it out.
Doesn't feel like it's a...
Yeah, obviously that, but I'm just trying to, it doesn't look like it, but, because since we reduced AB, that from B to D is definitionally smaller than from A to, from B to D is definitionally smaller than from B to A, so DC is reduced from that.
I definitely agree BD has to be smaller than BA.
So
Don't know that
DC
necessarily means CD has to be smaller than BA, because these two, because BD and CD, I don't see a reason why those would necessarily need to be the same length. You're absolutely right that DC and AB will have to be different lengths, but I don't see a good reason for why other than one looks smaller than the other. Because one looks smaller than the other won't quite cut it in one of these proofs, since our proof should be independent of picture. Let's get it. Any ideas?
Well, the problem, since we already know that DB was cut off on AB, we know that the second triangle is not the whole of the first triangle. So then if they're equal, the whole and the part will be equal, but that's impossible.
Yeah, I think the easier comparison, rather than trying to compare two lines from the different triangles, is just to compare the two triangles as a whole. And to say, well, this is saying that the triangle DBC is equal to the triangle ABC, but DBC is kind of cut off from the triangle ABC. It's only part of the whole triangle ABC. And we could use Euclid's common notion number 5 to say that can't happen. We can't have part of something be equal to the whole of something. And I think that's maybe an easier sort of comparison to make than trying to compare DC and AB, those two lines directly. Because those two lines are kind of harder to make a comparison between which should be longer than the other. So let's see, triangle DBC will equal the triangle ACB. The less to the greater. less to the greater, which is absurd. So Euclid is saying that the lesser triangle DBC being equal to the whole triangle ACB is an absurd statement. What do you think Euclid means by absurd here?
It contradicts itself, right? Can't be true.
Yeah, I would say by absurd, Euclid is just meaning this is a contradiction of the facts as we know it, or the common notion 5 at least. He's not saying absurd in the sense that like only an idiot would think that necessarily. It's just saying absurd here is kind of the same absurd appearing in a reductio ad absurdum, and it's just being used to mean a contradiction. And though Euclid doesn't explicitly say it, it's going to be a contradiction of common notion number 5. One that says the whole is always greater than the part. Here we have a whole triangle equal to part of that triangle, and that shouldn't be allowed to happen. And thus, AB is not unequal to AC, because that's what we contradicted. We said we assumed AB is not equal to AC, showed that led to a contradiction, and so that tells us then that AB is not unequal to AC, hence AB equals AC. So in other words, what we've shown is that if the angles at B and C are equal, it would have to be the case that the whole side from A to B must be equal to the whole side from A to C. Because if they're unequal, then we get that a lesser triangle, the whole triangle is equal to only part of the triangle, which is a logical contradiction. Any questions or comments about this proof? I had a follow-up question, but it was already in. But I was actually planning on asking why couldn't we have used the angle ABC with it equal to itself instead, but you all already answered that question for me partway through. So this proposition is famous for being the first one that Euclid uses a reductio ad absurdum proof, an RAA proof to actually prove, which is kind of why the main reason why I wanted to talk about this proof in particular. Because that's something we had last seen way back in Standard 9, and I kind of wanted to reintroduce it here as an example of one of these RAA proofs. Because while this is the first thing Euclid proves in this way, it's far from the last one. It uses a reductio ad absurdum more and more as you go throughout the elements. Assume the opposite of what you want to show, and then show that leads to a logical contradiction, or as Euclid might put it, an absurd statement. So that's it for Standard 15. Threw this in Standard 15 because it was also about the behavior of triangles, like everything else in Standard 15. But next up, we are going to flip over to Standard 16, another packet. Where I have two goals for Standard 16. I decided to title Standard 16 Constructability Successes. Because in Standard 16, we're going to prove that it's very possible to construct geometric figures in a way in a way we like to. We're going to show we can, in other words, bisect angles, and given a square, find another square whose area is double the original one. And then in standard 17, which will be the one after this, we're going to show that given 3 very similar problems to the 2 problems we're going to successfully do in this one, we're going to look at 3 problems that it turns out the Greeks couldn't do. And that remains enigmas for a number of years. So 16 and 17 are going to be heavily related. 16 is about things we can do. 17 is going to be about things that the Greeks at least could not do. So I'm going to jump right in on the second page to Proposition 9, in which Proposition 9 is going to say it is possible to bisect a given angle. So this introduces a new term, namely the term bisect, which is something we haven't yet seen before in the elements. And it's actually a term that Euclid himself never comes up with a definition for. So what I kind of like to do is to see, first of all, before we even prove this proposition, is can we come up with a definition for bisect? Let's see, can you see that on the video? Yeah. So I want to ask the question, what does it mean to bisect the angle CAB here? Well, I'll put it this way. Bisecting an angle CAB pictorially is going to look something like this. So what did we just do? In drawing this, I drew this line in a very particular way in order to make 2 things equal to each other. Which 2 things did I draw this in a way that made them equal?
So to bisect is to divide into 2 equal parts. So you took CAB, made CAB and DAB, which would be equal to each other.
Exactly. Here by bisect, we mean specifically take something and split it into 2 equal parts. Which in this case means to bisect an angle, CAB, means to sort of make 2 smaller equal angles that when combined would make CAB, namely CAD and DAB. So to bisect the angle CAB, this really means to draw a line AD between AB and AC so that angle BAD is equal to the angle CAD. In other words, it means to cut angle CAB into 2 equally sized smaller angles. So that's going to be our goal, is to show that given any angle of the form CAB like this, we can always find a way to bisect it, to find a line that comes down through the middle and cuts angle CAB in half, so to speak. So let's see if we can do that. So if you notice, our proposition 6, the one we just proved, was sort of a here are properties of pre-existing objects sort of proposition, meaning if we have a triangle where 2 angles happen to be equal, then we can say some more properties of the original. This one's going to be more along the lines of the first few propositions. That's of the form, here is going to be a recipe for how to construct something. In other words, how to construct a line from A to some other point that will cut this angle in half. So to start, we're just going to say let angle BAC be the given angle. And thus, it's required to bisect it. So, we've got our angle BAC. Our goal is going to be bisect it in the way we described below. First thing we're going to do is we're going to let D be taken at random on the segment AB. So in other words, we're given the segment AB. First thing I want to do is just pick any old point on it. Doesn't matter where, according to Euclid. I'm going to pick it like here. And then we're going to let AE be cut off from AC equal to AD. So in other words, pick a point on AC, which we'll call E, about here, such that the length of the segment AE is equal to the length of the line from A to D, which is something we should be able to do from proposition 3 again. Basically saying we have a longer line AC, a line AC that's longer than AD, cut AC off at a point E, where this cutoff line from A to E is equal to the length of the shorter line from A to D. Any questions or comments so far? So we've cut off AC and AB at 2 points, D or C and D, E and D respectively. And now we're going to let DE be joined via postulate 1. Let's see. Draw a straight line from AE to DE. We don't necessarily know DE has the same length as AE and AD. It depends on the angle, how far apart D and E are from each other. We don't necessarily know, same as, if that's the same though as the other two sides. But the next thing we're going to do is we're actually going to draw an equilateral triangle out of DE. So after DE, we're going to say, and on DE, let the equilateral triangle DEF be constructed. So we're going to form an equilateral triangle about here. Such that these three sides all have the same length. And what proposition or postulate is going to tell us we can construct equilateral triangles? Dr. Gerstle, please don't look at me. I don't want to have to answer this question. It's going to be our very first proposition in Euclid's Elements that tells us we can do that. Yep, that was the first thing we proved, is that on any line, including the line from D to E here, we should be able to construct an equilateral triangle. And then we're going to let AF be joined. Which postulate 1, once again, is going to allow us to do. I claim we've drawn a line that should bisect the angle CAB at this point. Which line have we drawn up here that you think looks like it's going to bisect the angle CAB? That's going to cut CAB into two equal-sized pieces.
AF.
AF. So AF is going to turn out to be the line that bisects the original angle CAB. And now we're just going to have to show that AF does in fact bisect it. And to do that, we're going to have to use one of our triangle equality propositions. So Euclid is going to say, I say, the angle BAC has been bisected by AF. For, since AD is equal to AE, and AF is common, DA and AF equal EA and AF respectively. So here, he's using the fact that DA is equal to EA. This line here is equal to this line. And that's by definition. We constructed the point, we picked the point E in a way that forced AE and AD to be equal. So EA and DA are equal. We also know that AF is going to be equal to itself. And finally, we also know that EF and DF are also going to be equal. And the base DF is equal to EF. How did we know those two sides are equal to each other? DF and EF.
Because the two sides of an equilateral triangle.
Bingo. It's because those are both sides that came about from this equilateral triangle DEF. And so we know AE is equal to AD, DF is equal to EF, and AF is equal to itself. And from there, Euclid's going to claim that these two triangles, AEF, is going to be equal to the triangle ADF. Thus, the triangle ADF is going to be equal to the triangle AEF. And which of our triangle equality propositions did we just use? We said AE is equal to AD, DF is equal to EF, and AF is equal to itself. So, which proposition is then going to tell us these two triangles have to be equal? Side, angle, side, 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 angle, or angle, angle, side?
Side, side, side.
Side, 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 because we've shown all three sides of these two triangles are equal. Therefore, the two triangles themselves are going to have to be equal. proposition 1.8, which is the side, side, side one. And so, the angle DAF is going to be equal to the angle EAF. Saying since these two triangles are equal, these two angles should also have to be equal. And then we're done. We've shown F, the line from A to F, has cut the angle from the angle CAB in half in a way that makes the angle CAF equal to the angle BAF. Using the fact that side, side, side tells us the angles of these two triangles, AEF and ADF, should all be equal to each other. And then, thus, angle BAC has been bisected by straight line AF. We found a way to cut the angle CAB into two equal pieces with this line from A to F. We used a bunch of other points and lines along the way to help us get there, but if we don't need those other points anymore after the fact, we can just erase them. And what's left is going to be a point F where the point F is AF is cutting this angle exactly in half into two angles of equal size. Any questions or comments about this proposition? So Euclid proved this one pretty easily, that the angle given any angle, you can bisect it by cutting it into two equal-sized pieces from his postulate pretty easily. It did rely on having to use side, 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 which is why this is proposition number 9. It relied on Euclid's side, 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 proposition number 8 in order to prove. But another problem that Euclid was very interested in was the idea of how can we trisect angles? In other words, given an angle, is it possible to find two lines coming out of that angle where all three of the angles made are all going to be equal to each other? We can cut an angle in half, but can we cut an angle into three equal-sized pieces, in other words? It turned out to be the case that this is one that Euclid struggled with for a long time. In the end, he gave up on it. This didn't make it into the elements at all. And in Standard 17, we're going to be spending a lot of time looking at this question of how can we trisect an angle using Euclid's postulates and common notions. And as it's going to turn out, the idea of how to do this is something that didn't just vex Euclid, it vexed geometers for thousands of years. But I think that's going to be a good point to call the class